Hello, we are not meeting in person today, so this recorded video is to continue our work with HY-8 to analyze culverts. So before we get into the video, I wanted to just make a couple of announcements. First of all, homework 1, which is that assignment that deals with flumes, culverts, and using HY-8, that assignment is due on Wednesday the 19th. And so we don't have class on Monday, and I don't have my usual scheduled office hours because the university is closed that day. So if you do have questions on the assignment, then you could get with me on Tuesday, or you could send me a message as you're working on it. Of course, the best way to get in touch, of course, is live through Teams. It's just easier for me to see what you're up to if it's an interactive thing rather than you typing an explanation. So I know I've mentioned all that before. Just wanted to reiterate the assignment is due. Upload it to Blackboard before class on Wednesday. So this video that follows is recorded from a previous semester, and it includes another example where you're utilizing HY-8 to do an iterative analysis. And we did kind of a similar thing in class on Wednesday when we were looking at the progressively larger pipe diameters that would be required to ensure that there's no overtopping at the culvert. So it's a similar thing with this next example, and I think both of these kind of set the foundation for what you need to do on the homework. Although, of course, then there's another mental leap on the homework as well because you're going to be doing a bit of design. So anyways, if you have questions, get in touch, and otherwise I will see you live and in class on Wednesday the 19th. Let's consider this second example. Okay, so this is the side view. This time, instead of being circular, this is a box culvert. And so you can see that it is rectangular with 1.5 meter width, 1.5 meter height. Its N value, talking about the material that the culvert is made out of, is 0.013. And that's a Manning's N value that corresponds to concrete. So in the material properties, when we set it up, we're going to say it's a concrete box culvert. Now, in this sketch, the first example, I told you the elevations. But in this case, we don't know necessarily like what's the mean elevation above sea level, but we know the slope of the culvert. And also that slope of the channel is presumed to match the slope of the culvert. And so we're going to have to come up with our own elevations and then calculate the upstream and the downstream, the downstream elevation based on the slope. So let's just say, for instance, if this invert elevation is 100 meters, we're going to have to calculate the downstream invert elevation based on a length of 40 meters and this slope. And then the downstream channel roughness is 0.05. Now there's two things that we're going to look at here. We're going to analyze with this culvert, then how much of a flow rate causes the headwater to get up to 2 meters. So we're kind of like stress testing this culvert to find out, if we have this is actually in place somewhere and we're a little bit worried about the water getting 2 meters deep. We want to find out what flow rate would cause the headwater depth to be 2 meters, and then the channel width downstream is 5 meters. And I think that this one is also a rectangular channel downstream. Oh wait, hold on. Channel width is 5. Okay, and then in part B, we're going to change the downstream channel to some different value besides 5 that will affect the tailwater. All right, so two different analyses here. Let's set it up together. We need to start from scratch here. We'll delete our existing model here. So File, Close. Well, you can save that if you like. There's so many different reports you can look at. But that analysis table will usually give us what we need to answer the questions. Does everybody here know how to take a screenshot? There's a button on your keyboard that says Print Screen. I think I had you do screenshots in the fluid mechanics lab. Right. So in the homework assignment, I'm asking you to prove that you've done an analysis. And so what you need to do for those screenshots in the homework assignment is take a screenshot of this. This is the input to the model. So print screen, you start up Word and paste the screenshot into Microsoft Word. So just as a quick revisiting here. All right, and then I'm going to crop out the part that's irrelevant so that it can zoom in on what is important. These side areas here aren't helping to address what was in the input. Okay, so since I've cropped that now, I can expand that and it's easier to see. So that's the input, and then the output, analyze crossing, it's this table. So print screen, and then this proves that you did the analysis, and it's the basis for the explanation that you provide. Like, for example, if it is asking, how big does the culvert need to be, this is where you could show, well, the input I gave you yields this output, and it shows that the those two 1.6 meter diameter circular concrete pipes only yield a tiny bit of overtopping at our design flow. So that's just, in essence, how to do the screenshots and submit what you've done in HY-8. All right, so close this one. We don't want to save it, and we're going to do a new crossing. This again is also SI unit, so once again we have to specify SI, and then culvert, new culvert crossing. All right, so interpreting this sketch, starting up in the upper left here, what flow rates, well, what does the problem say? What flow rates? It doesn't even specify. We don't know. So we just have to put in some flow rates and then see how high does that take the headwater. So let's just say 10, from 0 to 10. And we can put the design and maximum as the same thing. All right, the tailwater is rectangular. It's a rectangular channel downstream. And in part A, we're saying we're going to use this start value of a channel width of 5 meters. Okay, so it's a rectangular 5 meter channel. Bottom width 5. Channel slope 0.007. Okay. So channel slope 0.007. The roughness of the channel 0.05. Channel invert. Remember, what that's asking is what's the elevation here where the downstream channel matches the culvert. We haven't calculated that yet, but we can from the slope that's given. So if we assume that this elevation is 100 meters, then this elevation is going to be 100 meters minus 0.007 times the length of the culvert, which is 40 meters. All right, so how much lower than 100 is that downstream elevation? I think what we end up with is 99.72. Can someone double check? Yeah, that's right. Okay. $99.72. And while we're at it, let's go ahead and put that same stuff into the culvert. So inlet station of 0, outlet station of 40. So now with that we've defined the length of the culvert, inlet elevation 100, outlet elevation 99.72. Do you remember the picture of Colorado, the culvert where those 3 pipes were going under the road? In that picture, the invert elevation and the channel invert was the same. Like, because the water came out of the culvert and then it plunged down, and the river bottom was probably a good 4 or 5 feet deeper. But in both of these examples we've worked so far, the river matches up exactly with the bottom of the culvert invert. Okay. All right, so what else do we need to put in here? Roadway data. We don't really have an idea of how much height is there, and we're never going to get that far because we don't want to find out how much overtopping there is. We just want to find out what's going on when the headwater gets up to 2 meters. So all we have to do is we have to build the front side of that culvert so that it's at least 2 meters tall, because we want to find out what's happening hydraulically through the culvert on the way up to 2 meters. And so let's just say that the crest length, I guess it would probably be the same as the channel width, right? It said that the channel width is 5 meters. It's never going to matter because the water isn't going to overtop. You know, when the headwater is at 2, it's not yet overtopping, and so it's not going to use this weir flow data. So, I mean, I'll put these things in here, but it doesn't matter. The crest elevation has to be at least 102, so I'll just say 103. That's the only parameter that does matter, is making sure that the overtopping doesn't happen before we get to a headwater elevation of headwater depth of 2 meters. Top width, I don't know, 10 meters. Does everybody understand what I'm saying, why this doesn't matter so much? Because the question is just all about the headwater getting to 2 meters. And so we just need this height to be more than that, because we don't want to know what's happening with the overtopping. We just want to know what's the capacity of the culvert when the headwater is 2. All right, culvert isn't circular, it is now rectangular. So we'll put concrete box, and you'll notice that the span and the rise have units of millimeters. And so we're going to have to convert from the given data of meters and make it 1,500 millimeters of a span, meaning the width, 1,500 millimeters rise. Now again, the embedment depth is related to like if the culvert is embedded inside the front face of the side slopes, we'll just leave that blank. The Manning's N is talking about the roughness of the concrete, and we were told that the roughness is 0.013, which is a little bit rougher than this default value for concrete. So let's update that, 0.013. It's straight. And now the inlet configuration, you know, the angle of the wing wall can be changed. Let's just start with this default assumption of a 90-degree head wall. So the concrete is up against the face of the soil that is underneath the road, and we don't have the wing walls guiding the flow into the pipe. If we did, then the capacity would be improved a little, and we might try that. Let's look at, first we'll do the analysis with a square edge 90-degree head wall, and then we'll do the other one. We'll add one of these wing wall just to see how it changes the flow rate. All right, I think we have everything we need. We tell it how much water is going through there. We tell it the downstream conditions, how high the road is, the culvert parameters. We can click Analyze Crossing. And the question we're answering here is, what flow rate causes the headwater depth to be 2? So headwater elevation, you see 2.1. It looks like the discharge is 6. So if I want to know exactly what is the discharge when the headwater elevation is 2, I'm going to have to do that thing where I zoom in on the flow. So what I really want to do is I want to look at what's happening between 5 cubic meters per second and 6, because right now I don't know exactly what flow rate it is that causes the headwater elevation of 2. I just know that it's between 5 and 6 cubic meters per second, because this is below 2 and that's slightly above it. So let me close this and double click on the culvert. Let's make it from a minimum flow of 5 and the design and maximum flow of 6. Analyze that crossing again, and we have it going in much smaller increments, and here we have 2.01. That's pretty close to 2. And so what I can now say in words, I'm going to write this on the board, like the interpretation of our analysis here. when the headwater depth is 2 meters, the flow capacity through the culvert is 5.70 cubic meters per second. Now let's just double check in the problem statement and make sure that we've addressed what it's asking. So, what flow rate would cause the headwater depth to be 2 when the downstream channel width is 5 meters? Yes, I think that what this is saying is for the downstream channel being rectangular and 5 meters wide, then the flow rate through that culvert will be 5.7 when the headwater elevation is 2.01. And that's close enough to 2 that, I mean, if we wanted, we could say, well, let's reanalyze the culvert between 5.6 and 5.7 cubic meters per second. And I suppose we could get that elevation nailed a little bit better, but I mean, 1/100th of a meter is pretty close.
So what number did you change on the last data?
What I changed was the minimum and the design flow rates to zoom in, you know, like, because before when I was going from 0 to 10, the problem with that was that the table doesn't, I don't know exactly what's going on at the headwater depth of 2. I know what the flow rate is when the headwater depth is 1.8, and I know what is the flow rate that corresponds to a headwater depth of 2.1. I guess I could do my own linear interpolation, but it's actually, I mean, the behavior isn't exactly linear, so it's better just to zoom in by changing that to 5 and that to 6, reanalyze the crossing. Yeah, so depth 2, flow rate 5.7. And no overtopping. By the way, like, what if we made a mistake? Remember how I just had to, like, pick an elevation for the roadway? Let's see, where did I do that? Yeah, crest elevation. What if I said 101.5? I've accidentally put the elevation of the road too low. Now I'm going to have a bunch of overtopping flow, and I can never find out what's going on with the headwater. You know, the headwater never gets to a depth of 2 because the road is lower than that. So that's why I kind of just had to make sure that the roadway elevation was at least as high as 102. Even if I did 102.2, I think that'll probably be high enough to where all of the flow is going to go through the pipe and none of it is going to be overtopping. So what do you think? Do you like HY-8 so far?
It's not that bad.
Not that bad. In comparison to what?
I can't remember. I like water gems. That's a little confusing.
You like water gems?
Yeah.
All right.
It's just a matter of making sure you plug in the right numbers in the right spot.
Yep, that's what it is. All right, so let's do the part B. Part B was asking, all right, so find the rectangular channel width that will cause the tailwater depth to be 2 for the flow rate found in part A. Oh, that's so confusing. What does that mean? All right, so part B is saying, all right, for Q equals 5.70 cubic meters per second, how wide does the channel have to be for, okay, so B equals what for depth equals 2 meters? So what we're actually analyzing in part B is the downstream channel. And this is something I pointed out on Wednesday, but I'll show you again, this button where you can view the rating curve. So that rating curve tells you the relationship between flow rate and water depth. So what we're looking for in part B is we want to find out, all right, if we want the water depth to be 2 meters for the flow rate of 5.7, how wide does the channel need to be? So we're kind of like designing that downstream channel. Okay, so so far the depth, oh, this is zoomed in between 5 and 6. And so here's the 5.7. So 5.7, the water depth is only 0.898. So should we make the channel wider or narrower to increase the depth? We're saying we can tolerate a depth downstream of 2 meters. Right now, with as wide as the channel is, the depth is only less than 1. Let's make the channel narrower. So would a 4-meter wide channel be okay? What we're trying to do here is try and save the client money, because excavating a 5-meter wide channel is very expensive. Maybe, based on our tolerance for 2 meters of depth, maybe a 4-meter channel would be okay. So I change the bottom width to 4. I view the rating curve again. All right, so 5.7 flow. Now the depth is up to 1.08. I can make that channel a little bit narrower, 3. All right, 5.7 flow, depth 1.4. Oh, we're getting closer.
Don't go to 2. You'll
Don't go to 2.
It passes
Between 2 and 3? All right, so let's try 2.5. 1.7. All right, we're getting closer. I think I can go narrower than 2.5, 2.35. This is like the Price is Right in a way. All right, you want to get as low as possible without going over the depth. So you get the idea, right? This is iteration. And by the way, doing these calculations by hand, that'd be brutal, because you're solving Manning's equation for a bunch of different flow rates. You're solving the depth. And so it'd be like an iteration within an iteration. So, you know, this is an optimization thing where you're finding how narrow can the channel be and still have a depth that isn't too much.
As close as I can get it, it looks like around 2.2.
2.2? All right, let's try that. 2.2,
No.
5.7. Yeah, that is pretty tight.
That's what I
2.16?
Yeah.
Let's save some more money. 2.16. Now that is perfection. Well done, guys. You nailed it. It's like a dunk. All right, so I'm going to stop talking because I want you to try Culvert example 3 on your own. So I've got the problem statement here on the screen. You're going to do design, which is that iteration we've just been talking about, where you change things over and over again until it's good enough. Now this is a little bit different because we want the maximum headwater to be 7 meters when we're carrying 10 cubic meters per second. The channel is trapezoidal. The bottom width is 3. We have the roughness, 1-to-1 side slopes on that trapezoid. So part A is design a culvert so there's no overtopping. Part B is we can have 0.1 cubic meters per second of the 10. Excuse me, we can have 1 of the 10 go overtopping. No elevations are given, so you will have to assume one and calculate the other. All right.
So what are the limits of this program?
What do you mean?
Like, is there any limitations to it, or
Oh, there must be, right?
or
It only designs culverts?
does it account for like the
we've got that same 99 point. All right, we're almost out of time, so your design may look different from mine, and that's okay. When we're doing design, we can all get different answers. When we're doing analysis, we should all get the same answer. But this is saying design a culvert so the maximum headwater is 7 meters. So I just put in 1,000 millimeters, and it looks like the headwater gets up to 7 when only 5 is getting through the pipe. So I need to make my pipe bigger because I get to headwater 7 before I achieve 10 cubic meters per second through there. So now it's the optimization game where I'm playing around with the diameter. Would 1250 be big enough? So now I achieve 8 cubic meters per second before overtopping occurs. So still not quite big enough. Let me close that and optimize a little bit more. What about 1400? And analyze crossing. Now that's big enough. It is big enough because when the headwater gets up to 7 meters, then I can get 10 through there. So I could make it a little bit smaller, but 1400 is a nice round number. So let me just say that my answer to the first part is the culvert has been designed so that so the headwater depth is 7 when 10 is getting through the pipe. Now B is a little more relaxed. It's saying, well, 1 of the 10 can overtop. So now that means my pipe can be a little bit smaller. And so if we have, a rugged paved top, then we could maybe see what happens at 1,300 millimeters, analyze the crossing. So at 1,300, yeah, it looks like at a depth of 7, 9 is going through the pipe, which means, I wonder where the roadway. So it's getting a little high. So I'd need to optimize that a little bit further. But I think you get the idea that, the water can go one of two places. It can go either over the top of the roadway or it can go through the pipes. So on the homework assignment, you get some more opportunities to play around with HY-8, and the tricky thing, as always, is interpreting the geometry and kind of trying to understand the problem statement. And so hopefully these examples gave you an initial exposure